Euler's formula is an identity found everywhere in complex analysis and is used to define many functions in the complex numbers. The foundational identity is e to the I theta equals cosine theta plus I sine of theta, where theta is a constant and I is the imaginary number I. The constant theta can also be a complex number itself. I'm going to be proving this identity using Taylor series in this video. So here are the Taylor series we need for this proof. We are assuming they are all centered around x equals 0. The Taylor series of e to the x centered around x equals 0 is the sum from n equals 0 to infinity of x to the n over n factorial, which turns out to be 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. There's a generalization of this, which is the Taylor series of e to the ax, where a is a constant. The Taylor series of e to the ax is the sum from n equals 0 to infinity of ax all raised to the power of n over n factorial, which turns out to be 1 plus ax plus a squared x squared over 2 factorial plus a cubed x cubed over 3 factorial, and so on. We will also need the Taylor series of cosine x and sine of x, since these two functions show up on the right-hand side of Euler's formula, except in terms of theta. The Taylor series of sine of x, centered around x equals 0, is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so on. The Taylor series of cosine of x is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and so on. These are all the Taylor series that we need for the proof. So here's how we do the proof. We start with the expression e to the I theta, which is the left-hand side of Euler's formula. We write out its Taylor series expansion, which is the sum from n equals 0 to infinity of I theta all raised to the power of n divided by n factorial. This is using the Taylor series expansion for the function e to the ax, which we established earlier. This turns out to be 1 plus I theta all squared over 2 factorial, and so on, which simplifies to 1 plus I theta plus I squared theta squared over 2 factorial, and so on, if we expand the expression in the numerators of each term in the sum. Since I squared equals -1, we can rewrite the I squared theta squared over 2 factorial term as negative theta squared over 2 factorial. I cubed equals -I, so we can rewrite the I cubed theta cubed over 3 factorial term as negative I theta cubed over 3 factorial. The integer powers of I are cyclical and repeats itself every 4 exponents, so we can simplify the integer powers of I with a predictable pattern. I to the 4th equals 1, so we can rewrite I to the 4th theta to the 4th over 4 factorial as theta to the 4th over 4 factorial. I to the 5th equals I, so I to the 5th theta to the 5th over 5 factorial equals I theta over 5 factorial. I to the 6th equals I squared, which equals -1, so I to the 6th theta to the 6th over 6 factorial equals negative theta to the 6th over 6 factorial. I to the 7th equals I cubed, which equals -I. So I to the 7th theta to the 7th over 7 factorial equals -I times theta to the 7th over 7 factorial. Since the powers of I repeats itself, the series will continue on in a predictable manner. The terms with even exponents of theta will always not have an I term before it, and the terms with odd exponents will always have an I term before it. The series will also follow a pattern of 2 terms with positive coefficients followed by 2 terms with negative coefficients, then 2 positive, then 2 negative, and so on. We can collect all the terms without an I before them to form the real part, and take all the terms with an I before them and factor out the I to form the imaginary part. After doing this, we get the original series separated into its real and imaginary parts. If we look at the first series in the expression, you'll notice that 1 minus theta squared over 2 factorial plus theta to the 4th over 4 factorial minus theta to the 6th over 6 factorial, and so on, is the Taylor series for cosine of theta, so we can replace that part of the expression with cosine of theta. If we look at the second series in the expression, the one that is multiplied by the I term, you'll notice that theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial minus theta to the 7th over 7 factorial is the Taylor series of sine of theta. So we can rewrite that part of the expression as sine of theta, and the second term becomes I sine of theta. We started with e to the I theta, and after doing a bunch of steps, we ended up with the expression cosine theta plus I sine of theta. This proves that e to the I theta equals cosine theta plus I sine of theta, which is exactly Euler's formula. And this is what we were trying to prove in the first place. So e to the I theta equals cosine theta plus I sine of theta. As I said, this is a very important identity for most of complex analysis and shows up all the time.